We are very happy to have this opportunity of hearing Professor Debabrata Maiti today for many different reasons. The first and foremost of which being that he is our own student. Debu was a student here. He graduated in 2003 with a silver medal from our department. Then he moved on to Johns Hopkins University for his PhD, and he was a postdoc in MIT. He was trained as a bioinorganic chemist. Well, before that, when he was here in IIT Bombay, his MSc project was in coordination chemistry with Professor Lahiri. Now, when he came back and started his own research career, what he has done is that he has taken inspiration from biology to do novel reactions. And one of the biggest challenges nowadays is all of us have studied organic chemistry, like it or not, at some stage or the other. And maybe you have realized, maybe you have not realized at that time, that one of the biggest challenges is that you have a CH bond, you transform that bond to something else. That's not so easy. So that has been an area of emphasis across the world. There are hundreds of groups working in it. There are very few groups that have made as much of impact worldwide as Debu's group has. So that is his claim to fame. I will not list his awards and accolades for two reasons. First is there are too many and still they are incomplete. Second is there are people who get distinguished by awards and there are people who add distinction to the awards. We feel that Debu belongs to the second category. He's also an excellent teacher, outstanding speaker, as we are going to learn very soon. So without further ado, Debu, could you please?
Hello, good morning everyone. Am I audible at the back? Okay, thank you. Thank you, Anindya, for this sweet and kind introduction. I think you have already created enough pressure. If you have not created enough before in the department. So I don't know whether I can handle that much, but I will try my best to discuss part of the research and the activities that is going on in our department or in my group. Okay. So at this juncture, I will first like to take this opportunity to thank our department, institute, IRCC in particular for giving me this wonderful opportunity. None of this, as it's not a matter of talk or matter of mentioning, none of this would have been possible without my students. I mean, some of them are here, some of them of course have graduated. So thank you for showing up, thank you for your support, thank you for all the hard work that you have put up, which enabled me to be here today. So I'll discuss, as Professor Datta was mentioning, some of the approaches that we are trying to elaborate in our laboratory. I'm sure all of us are familiar with biological systems. Chemistry wise, essentially it is very simple if you want to look at it. There are metal containing sites in biology, there are non-metal containing sites where no metal is there. Here I have taken one example. It's a very important enzyme known as cytochrome P450. I'm sure you have heard of. This causes many good things as well as many bad things. Let's say if you are taking a medicine, if medicine is not effective, partly it is due to this enzyme, because this enzyme can degrade, can react with the medicine and can lead to pathways which can destroy the medicine before it does its job. Okay. So this enzyme cytochrome P450 has a ligand which holds the metal center. This is the metal center, this is the ligand. Now this ligand and metal center ensures that the organic substrate which is sitting right in front of it, it's a gigantic organic substrate and it has many carbon-hydrogen bond. As you know, the organic molecules by definition are having many carbon-hydrogen bond. But the beauty of this enzyme simply is, despite having many different carbon-hydrogen bond that is present into this molecule, selectively it can promote functionalization or reaction at only one site. Once again, if you take any organic molecule, you will see many different sites where your reaction can happen. But the overall design of the protein, active site as well as the orientation of the substrate is such that it is oriented in one way and only one carbon-hydrogen bond, despite having, let's say, 100 different carbon-hydrogen bond where reaction can happen, this is happening very selectively and efficiently. Now, as chemists, we are really intrigued how any of us can promote such levels of selectivity. If we look back, relax and look back, how enzyme essentially is doing this sort of selective transformation, we immediately realize there is a binding pocket. It's like a lock and key mechanism. You have a lock and you have a perfect key for that, right? But this sort of perfect orientation in for synthetic chemists like many of us is not that very easy. So in order to achieve this sort of high selectivity as well as very efficient reaction, what some of us or many of us in the domain now, including some of us in our department as well as all across the world, what we are trying to do is we are trying to take the organic substrate and attaching this ligand. So this ligand here is not attached with the organic substrate, but here we are attaching with the ligand, attaching with the organic substrate, we are attaching the ligand, and then the metal is placed. Now, depending on the designing of this ligand or designing of this catalyst, we can selectively activate either this position, that position, that position, or that position. So essentially, we are indirectly trying to mimic the way nature is doing the chemistry. So the selectivity factor is governed by the designing of the ligand. How we design the ligand will dictate in synthetic setup whether we are going to get selective transformation or not. Okay, that specifically is going to be the the design of the first part or this part of my talk. So, for example, you must have heard of amino acids. There are many amino acids, essential amino acid. One of the essential amino acid is leucine. Leucine, is a very important amino acid, naturally occurring. But if you look at, if you don't want to really get into too much details, this is an amine and this is an acid. This is acid unit, this is amine unit. You have one carbon center, second carbon center, third carbon center, and fourth carbon center. Each of these centers are having carbon-hydrogen bond. So therefore, you can imagine there are many carbon-hydrogen bond into this molecule. What we have done is simply we have taken this ligand, this over here, it's called pyridine carboxylic acid, it's the name of the ligand. We have attached with this amine. So this simple designing has allowed us to activate or to touch this carbon-hydrogen bond selectively. So we have carbon-hydrogen here, there, as well as there, and most importantly, this is the one which is the farthest from the amine group. This is closest, this is closer, this is little far, this is the farthest one. If we are designing and attaching this ligand with this organic substrate, then selectively this distal, so-called, these are the proximal position, this distal position can now be activated. Activated meaning this metal can be inserted over there. Okay? This is a crystal structure clearly showing that this metal center is inserting at the terminal position. So metal is inserting selectively at that position, not on here, there, or there. Once the metal is inserted, we can do the chemistry subsequently at that site selectively and efficiently. Okay? And we are able to do that. For example, here we have shown how an arene group can be inserted into the organic molecule. Once again, this amino acids, which is a very useful building block and it has many different sites, selectively by designing this catalyst and attaching with this organic substrate, we can control the efficiency of the reaction as well as the selectivity of the reaction, just like what we see essentially in the enzyme setup. Well, another type of molecule, if you would have remembered from your undergraduate days, that there is aromatic ring, right? So there is aromatic ring. This is the aromatic ring. Two types of organic molecule roughly you can think of. One is aliphatic, where no aromatic ring is there. Another is aromatic ring containing substrate. Now in aromatic ring, you have different positions. So this is one position, this is another position, that is another position. So all these three positions are different. They are different in their way of working. Okay. So what we have been essentially trying over the last few years, that to design the ligand or template which will be attached with the organic substrate and will allow overall design to activate and functionalize a desired position. For instance, we were working, along with many others in the domain, were working to design the template so that this metal which is attached with the template can be selectively inserted at this second position, or so-called third position, so-called meta position. So what we tried essentially is to have this template or ligand so that delivery of the metal can be done at this position. We have been also working to design the ligand so that this whole molecule is wrapped around and the metal which is attached with the template can then be delivered selectively at this position. So once again, you have arene ring having 3 different positions. Selective designing allowed us to insert the metal at the distal so-called third position or meta position or para position. I will go very fast. So this approach has given rise to this template or this ligand designing. This is the one which we have designed, and selectively only this meta position or 3 position can be touched and functionalized. Okay. We have been also designing this ligand for the para-selective functionalization. That means selective reaction at this position, not at that position or this position. Selectively reaction is happening at the para position. Okay. So I will skip the mechanism. What we have essentially shown that this is one of the ligand or one of the catalyst ligand, I would say, template which we were able to synthesize, and this is now marketed, although we have not taken patent for this one first. We have published, so they have went on without giving us too much of royalty, but then for this one we have taken patent and we were able to do the technology transfer through IRCC. So we are again, this is the one which is now available from TCI. So these are catalysts. It essentially gives you an opportunity to do the reaction selectively in an organic molecule. Okay. If you attach this one, you will get the third position. If you attach this one, you will get the fourth position. Okay. And therefore, overall, this gives us an opportunity to do many different diversification. For example, these are the common drug or common medicine we take on a regular basis. Diversification of these drugs can be now done very easily. So-called late stage functionalization, for example. You take a complex molecule and you introduce the moiety of your choice very rapidly within different positions by utilizing these template or catalyst. Okay. These are some of the other drugs. Again, these are marketed drugs. You can take it, modify it, and then you can further study the structure-activity relationship. Not only you take the drug from the market, you can synthesize drug by utilizing this technique. Both you can diversify the drug as well as you can synthesize the drug. In addition to drug, it could be agrochemicals and pharmaceuticals that can be modified. There are some of the natural products which naturally are occurring, but you may need in very large quantity. Once again, that can be done by utilizing this strategy. Maybe I can again come back in the next talk, but again I want to emphasize the point that none of this work is really directly due to me. It's really due to my student. They are the one who has designed, failed and succeeded. Many more efforts I'm sure they will put. I'm really happy to represent on their behalf, and again all of my collaborators, some of them I have mentioned, Professor Lahiri, Shinoj, Rajaraman particularly for computational studies, Professor Arnab Datta as well as Anindya Datta, we were working on quite a few projects now. So all of them, thank you very much. And my Department of Chemistry, IDPCS, where I am also associated, IRCC and all the funding agency, I'm really grateful for their unconditional support. Thank you for your kind attention. Maybe I'll go to the next talk and then I'll try to take your question. Okay, thanks. Okay. So in the first talk, what you have seen essentially is how selectively you can take an organic molecule and selectively you can functionalize one of the position, right? If this is the organic molecule and you have, let's say, 5 different positions available, selectively you want to react at any of these positions, you can do it by designing the catalyst. Okay? So the design controls the selectivity. Once you are able to, let's say, achieve this selectivity and you are able to functionalize a molecule, also sometimes it becomes essential that you remove those functionalizations. Let's say you introduce a particular group and then you want to remove it, right? Just similar to, let's say, making a building and demolishing a building. Sometimes you need to make a new house. If the house is old or you don't require the house anymore, you need to demolish it. So the strategy should exist for the demolition also. And the demolition strategy, as you know, is as important, perhaps sometimes even more important than the building one. So this is what we also try to do, and it has good effect in terms of its application. For instance, we have heard of aldehyde group. Aldehyde group is basically having carbon, hydrogen and oxygen moiety. Okay? So in organic molecule, you have this sort of functional group. In the first part, I was trying to tell you how you can introduce the aldehyde group selectively when you have many different carbon-hydrogen bonds. Now I am trying to tell you how you can remove those functional groups that you have introduced by many different ways. How can you remove it so that you now get a relatively simpler molecule? Okay? Why one would like to do that? For example, if you have fatty aldehyde, there is an enzyme indeed that can convert fatty aldehyde into alkane. This alkane means, it's a fuel grade alkane. So from the natural source of fatty acids, fatty aldehyde is synthesized from fatty acid, biosynthesized. So if you take fatty acid, directly you can get alkane, which is again, it's a high quality alkane. Some of these are perhaps the purest you can get. So if you can remove the functional group, introduction of functional group is important, but if you can remove it, it becomes, if not equal, I would say almost as good as the original transformation of introducing it. So what we have been doing, we are taking a metal catalyst, some of the designing we were doing, so that this functional group such as aldehyde acid can be engaged in the reaction and then it can be removed. Okay? That's what we were trying to do. By doing so, what we also realized that we are generating carbon monoxide from aldehyde. Of course, if you look at holistically, nobody should generate perhaps carbon monoxide or carbon dioxide, but in chemistry world, all of my colleagues as well as students should tell that's also an effective transformation. If you can generate carbon monoxide from aldehyde, it gives you an opportunity to use organic chemical directly, where carbon monoxide can be taken from one organic molecule and it can be utilized in another one. For instance, over here, if you are taking this aldehyde where carbonyl unit is there, this carbon monoxide can then be introduced for another constructive purpose. That allows us not to take the carbon monoxide cylinder in laboratory and use it. Of course, it brings the sufficient hazardous implication if you are trying to use the carbon monoxide gas. Usually you are going to lose a lot of gas and it's under, usually it's also having some pressure. Dealing with it is always a big problem. But if you have a reaction where this sort of, let's say, aldehyde moiety which has carbon monoxide in it, if you can transfer from one set to another, you can then utilize the carbon monoxide directly right over here in one pot. Also, what it allows us, this sort of strategy, it allows us to do a reaction which was not possible. For instance, over here, if you do not have this aldehyde group, the desired reaction cannot be done in a way that you are projecting. Okay? So this so-called Diels-Alder reaction you cannot do if you do not have this aldehyde moiety. Now once you do the reaction, you may not need it anymore. In this case, you don't want it anymore, so therefore it can be removed. Okay? I will repeat, what I am trying to tell you is it is important to introduce a new moiety in the organic molecule. Also, it is important to remove it. We have devised a strategy by which you can remove, let's say, aldehyde unit or the carbon monoxide of the aldehyde unit or carbon dioxide of the acid. Okay, so we by utilizing this, we have synthesized also a number of important molecules, which the strategy of which is essentially based on the fact that we can take the benefit of this aldehyde group. Okay. Not only aldehyde, I am sure all of us are familiar with alcohol unit, like for example, I would say ethanol. So from ethanol, if you can get methane, that could be considered as very important challenge or important transformation. If you are able to generate methane from ethanol, that essentially means that you are able to take out the CH2OH or the alcohol unit from it. Okay, that gives us again an opportunity to generate fuel grade alkane from many different alkane that we can have. Okay, so this is what we were able to do with a suitable catalyst. We were able to remove the carbon monoxide to get the alkane. So alcohol goes to aldehyde and then it gives you the alkane. This strategy can also be incorporated in many natural product synthesis. Again, without this strategy, sometimes what happens, you cannot do the synthesis of complex natural product very easily. This allows this building as well as building the functionality as well as removal of the functionality allows you to do the reaction in a way where a chemist can play with their toolbox. Not only aldehyde or alcohol, the cyanide, as you know, of course we are maybe scared of potassium cyanide, not that every cyanides are very dangerous. Cyanide is a very important tool for chemists. The removal of cyanide, like organic cyanide, inorganic cyanide are, let's say, potassium cyanide, sodium cyanide, which is definitely can cause havoc, but cyanide group or the nitrile group, so to speak, nitrile group in organic molecule is very important. They have many usage, many drugs molecule, many agrochemicals, you have the cyanide unit. If you can remove the cyanide, then you have a strategy which you can utilize at ACE. You can oversee how to synthesize a complex molecule by introducing a particular functional group such as cyanide and then by removing it. Okay. So for instance, this alkylation reaction or this functionalization of this molecule was only possible if cyano group was there, or cyano, or I would say nitrile group was there. Now this nitrile group, if you can remove subsequently, then you can get a useful molecule. Once again, this particular reaction, if you are having a nitrile moiety present in that organic molecule, this reaction becomes feasible. Otherwise, this reaction will not go. But once you do the reaction with the help of certain functional group, you would also like to remove it at the end. So this strategy that we have developed allows us to do that. I'll skip the mechanistic cycle. Overall, what we were able to show is the metal is able to interact with this cyano or nitrile group, and then it is able to insert or introduce the metal in a way so that nitrile group can come out of the organic molecule. Another related thing is, not only you remove the functional group, while you remove the functional group, can you put two organic molecules together, right? So let's say you are working with ethanol. You have CH3, CH2OH. You want to remove that CH2OH group so that you have alkane such as methane. Now what if you are not happy with methane? You want to make it, let's say, propane, butane, hexane. You want to couple two things together. While you remove, you want to couple them together, right? So this strategy that we have developed allows you to do that. Here we are removing the acid group, carbon dioxide, in the form of carbon dioxide. Once again, removing carbon dioxide from an organic molecule, one may think that it is environmentally hazardous, but I would say the benefit that we are getting out of it is much more important than removing carbon dioxide. As I was trying to tell also, that carbon dioxide that is being removed can also be utilized for another reaction. In any case, what we were able to show in this particular case, that we can remove the carbon dioxide from this acid unit, and two of these units can be put together to give rise to the very important organic molecule. Okay, so I think I'll skip and I'll come to the very important slide once again, and that is to thank my student, thank my department, IRCC and our institute, and also the committee for finding our work suitable for giving this talk today. Thank you very much.